All right, well, welcome back. Hope you took a nice little break there. So we are still in week 13, and we are now backtracking in the second part of our lecture for week 13 to cover carbohydrates, which in fact is chapter 13, as well as a very small section in chapter 18, section 2. All right, so 18.2. So without further ado, let's continue on to carbohydrates. Introduction. Let's start with an introduction to carbohydrates. Carbohydrates. They are also known as sugars, as you are well aware from your grade school science classes. They are an abundant biomolecule. More than 50% of the carbon in organic compounds, in fact, is found in carbohydrates. Plants use photosynthesis. The equation for photosynthesis you see below. They use it to store energy in glucose. Glucose is, of course, a simple sugar. So this is an equation that you remember from your days in grade school science, probably. The equation for photosynthesis, plants take in carbon dioxide and water and energy and convert the carbon dioxide and water into glucose C6H12O6 and oxygen. So we in fact do get oxygen from the plants. They're crucial to our oxygen supply. So you should be familiar with this equation for the photosynthesis of glucose. Okay, so where do we go from here? Well, carbohydrate classifications. Carbohydrates, they are a large class of naturally occurring polyhydroxy. Right, so think about what that means. Many hydroxyl groups, polyhydroxy aldehydes and ketones. Right, so in this chapter, you're seeing why we spent all that time talking about the organic compounds. Okay, so carbohydrates, they're polyhydroxy. We're going to see a lot of OH hydroxyl groups, and we're going to see aldehyde groups and ketone groups also. Carbohydrates are grouped into three classes. Monosaccharides, they are the simplest sugars. And monosaccharides are what serve as the building blocks of larger molecules. An example of a monosaccharide would be glucose. Then we have the oligosaccharides. Oligosaccharides contain anywhere between 2 and 10 monosaccharides that are bonded together. The building blocks of these oligosaccharides are monosaccharides. We call them residues. Okay, so if your oligosaccharide has just 2 residues or 2 monosaccharides, then we call it a disaccharide. If there's 3, there's a trisaccharide, etc., etc. And an example of an oligosaccharide, which is a disaccharide, is sucrose, as a matter of fact, and we'll see it later on. And then we have the polysaccharides. Polysaccharides contain more than 10 residues. Residues, again, being monosaccharides. And an example of polysaccharides would be complex carbohydrates. And we're going to, again, see those near the end of our discussion on carbohydrates. We'll cover each of these individually. Okay. Monosaccharides, let's begin with them. All right, so we said that they are also known as simple sugars. And They are the simplest carbohydrates. Monosaccharides begin with 3 carbons. All right, so they contain anywhere from 3 to 7 carbon atoms. They are in turn classified by the functional group they contain. A sugar that contains an aldehyde is known as an aldose. Okay, aldose. ALD for aldehyde. And a sugar that contains a ketone is known as a ketose. Okay, so ketose, ket meaning ketone. Okay, and the OSE, sugar, indicates a sugar. So this is what we're talking about. This would be the very simplistic structure for any monosaccharide. All right. So some of them we said have aldehyde groups. All right. So here we have a monosaccharide. Okay, simple sugar, can have anywhere from 3 to 7 carbon atoms. Okay, so here we see one. There could be some more in here, and there's another one here. All right, so minimally it has to have another one in the center. Okay, that would be 3, and it could have as many as 5 in the center. All right, but what we're looking at here is the functional group. You recognize here the aldehyde functional group. And if your monosaccharide has an aldehyde functional group, we call it an aldose. So the other functional group that we see in these polyhydroxyaldehydes and ketones, these monosaccharides, is the ketone functional group. And here we recognize the carbonyl. Okay, let's see if we can circle it here. The carbonyl of a ketone. On one side we have a carbon, right? And on the other side, this means the number of carbons. Okay, so if we have a carbonyl that is a ketone in our monosaccharide, then we call it a ketose. Okay, so this is why we studied all those functional groups in the earlier chapter, so we could put them all together for these remaining chapters. All right, more on monosaccharides. So again, we said monosaccharides, what are they? They are polyhydroxy. So in addition to the ketone group or the aldehyde group, we're going to see a lot of hydroxy groups. And what else did we learn? They have 3 or more carbons, between 3 and 7 typically. So let's look at some of the more common monosaccharides. Let's begin with glucose. Glucose is an aldohexose, and we're going to see where we get that from. We see the aldo in there. We'll see shortly about that hexose. It is a monomer, okay, or is a residue for starch and cellulose, and it's a major source of energy. So this is its structure. All right, so think about what we said a monosaccharide entails. It's a polyhydroxy ketone or aldehyde. So let's look at this glucose, all right? We said it's an aldose, all right? So we see right up here, we see the aldehyde functional group. Additionally, right, we have to have 3 or more carbons. So we see 1, 2, 3, 4, 5, 6. So it's a 6 carbon monosaccharide. And you can see the polyhydroxy. Look at all these hydroxy groups, these OH groups in it. Okay, so this is a very common monosaccharide. And then we have ribose. Ribose is also an aldose. It is a component of ATP, coenzymes, and RNA. What does it look like? Okay, an aldose. All right, again, meaning it has an aldehyde. It's a monosaccharide, so it's a polyhydroxyaldehyde. Look at all these hydroxy groups. All right, does it fit the other definition? It's got to have at least 3 carbons. All right, 1, 2, 3, 4, 5 of them. So yes, it does. And here is the aldehyde functional group. Okay, polyhydroxyaldehyde. And then we have fructose. Fructose is a ketose. All right, so its structure is going to look different. It's not going to have an aldehyde. It's going to have a ketone. Right? Fructose is present in corn syrup and fruit. Okay, so notice the difference. We don't have that aldehyde at the very top of the structure. Instead, we look down and whoa, here we go. Here's our carbonyl of our ketone. On one side, we have an R group, an alkyl group, right? And the other side, we have a carbon too, right? Alkyl groups, carbons, right? There they are, one here, one there. Okay, so it is a ketose. All right, hang on and you'll see where we're getting these other names from, these additions to that. Okay, naming monosaccharides. Carbohydrate nomenclature. We have gone through all the functional groups in organic chemistry in previous chapters, and with every one we've gone through the nomenclature. How do we name them? And one of the commonalities was that we used this IUPAC nomenclature. Well, carbohydrate nomenclature, what can I say about it? Well, it's unique, okay? It is unique to a certain segment of chemistry known as sugar chemistry. And sugar chemistry does not name monosaccharides using the IUPAC rules. So we've got a whole different set of naming rules for monosaccharides. Monosaccharides, their names end in OSE, okay, which means sugar, all right, OSE. And monosaccharides, not only are they classified by whether they have an aldehyde or ketone group, okay, so they're classified by the carbonyl that's present, either the aldehyde or the ketone. So they're either an aldose or a ketose, as we saw, right? Okay. They're also classified by the number of carbons that they contain. If they contain 3, they're called a triose, okay? Tri meaning 3, ose, sugar, okay? Tet for ose, all right? Sugar, so for carbon or 3 carbon sugar, etc., etc. And then, all right, so they can be classified individually. We could simply say, oh, that's an aldose, all right? That's a triose. Okay, or that's a ketose, that's a tetrose. But they're also classified as a combination of these two, both. All right, so you put both parts of this name together. And so if it's an aldehyde and it's a 3-carbon aldehyde, you're going to call it an aldotriose. So now you're seeing where those names on the previous slide came from. If it's got the keto group in it, all right, and it's a ketose and it has 3 carbons, well, it's a ketotriose, etc., etc. So put in this table so that you can see how these names are developed. All right, so we've already seen, all right, so the type of name here. All right, so the name, we can get it from simply the functional group that it has. So if we're talking about what functional group do we have and we see it has an aldehyde, we call it an aldose. All right. If we're naming simply again by functional group and there's a keto group, then we call it a ketose. All right. But then we also classify and name a carbohydrate by the number of carbons. 3, we call it a triose. 4, tetrose. 5, pentose. 6, hexose. 7, heptose. You should see a commonality here. Remember the alkanes and those the names for the number of carbon atoms, the parent, right? Heptose for 7, octose for 8, nonose for 9. All right, and then we can name the monosaccharide using both parts. We can describe the functional group and the number of atoms. Okay, so if you have an aldehyde functional group and there's 3 carbon atoms, well, then it's an aldotriose. Okay, if you have an aldehyde functional group and 5 carbons, then it's an aldopentose. How about a ketone functional group and 7 carbons? It's a ketoheptose. Okay, all righty, very good. Moving on, let's do some examples. Let's see if you can figure out. Okay, so let's look at this and we see, first off, let's pull in everything we've learned. We look at this compound and we see that it is got a lot of hydroxyl groups on it, right? So it's a polyhydroxy. And there's also an aldehyde group, right? So this is a monosaccharide. So we would call it an aldose, all right? But how many carbons? 1, 2, 3, 4, 5. So it would be a pentose, all right? So putting everything together, it's an aldopentose. All right, let's look at this one here. And again, we see that it's got a number of hydroxyl groups, so polyhydroxy. And the functional group that we see this time is a carbonyl, right? With 2 carbons, 1 carbon on either side. So it's a ketone. So this is a ketose. And so we can either classify it alone as a ketose, but let's put in the carbons. 1, 2, 3, 4. So that's tet, right? So it's a tetrose. Putting it all together, this is a ketotetrose. Okay. Now, time for you to try it yourself. All right, I'll give you a little bit of help here. So in this particular problem, you're going to name each of the following monosaccharides as either an aldose or ketose. And then in addition, you're going to use the other part. You're going to use the number of carbon atoms. So you're going to use both of those aspects. And here they are. There's 3 of them for you to try. All right, so remember what you're doing. Classify it first as either an aldose or a ketose. All right, so look for that functional group. Okay, count the number of carbons and name it via that and put it together. All right. Okay, again, I need the timer. I need the Jeopardy timer here, the theme song for this. Okay. All right, let's go through them one by one. Our very first one, we see what functional group? Okay, if you saw this one right here, right? That is an aldehyde. Okay. So this would be an aldose. 1, 2, 3, 4, 5. So it would be an aldopentose. Our second one here, again, we see sticking out right here. We see an aldehyde. So this is an aldose, right? And how many carbons? 1, 2, 3, 4. So this is an aldotetrose. And our last one, we see a carbonyl. Okay, it's not an aldehyde. Right? And then we have a carbon on either side. So this is a ketose, and there's 1, 2, 3 carbons. So it's a ketotriose. Notice that the hydroxyl groups are not always expanded. All right, so everything that we talked about up to this point with organic compounds holds true for the carbohydrates. Okay, you may see totally expanded structures. Okay, or you may see condensed, or sometimes some things in between. All right. Okay, again, practice makes perfect, so make sure that you do those problems in your textbook. Okay, so we move on to Fischer projections. Fischer projections, they are a means that chemists use to represent three-dimensional structures of molecules on a flat page. Remember back to when we talked about the carbon atom and its 4 bonds, all right? It had dimension, all right? When we draw it on the paper, when we read about it in a book, it is flat on a page, but we know in reality that it's 3-dimensional. So we have some bonds going behind the plane of the paper, right? And some coming out at us, some in the plane of the paper. So let's show you what a Fischer projection does. Okay, so it's a way for us to represent a 3-dimensional structure on a flat page. So we start over here with the 3-dimensional structure. Okay, all right, a carbon with just 4 different groups attached to it. Okay, and remember, tetrahedral structure, 109.5 degree bond angles between each, okay, of these bonds. And so we talked about these structures that show dimension when they're solid lines, right? That means it's in the plane of the screen, okay? When they're dashed, it means it's going behind the plane of the screen. And when they're wedged, it's coming out at you, okay? So notice how this carbon is being shown, right? So we've got 2 in the plane of the screen, and then we've got 1 that's going behind and 1 that's coming out at you. All right, so that's how you're holding that carbon, if you could hold it in your hand with those 4 different groups. And we're going to smush it flat. Okay, so we're going to take it and imagine pressing that carbon down so that it is flat. And if we do that, then this Z that was coming behind, or which was going down, right, behind the plane, right, is now flat. There it is, and there's our Y, okay, which was coming out at us, right? This is going behind, and then our W and our X are flat. So we've flattened everything, okay? All right, and now let's flip it up so that we're looking at it, okay? And here it is. This is a Fischer projection. So we've taken a molecule that's in 3 dimensions, and we're representing it, all right, as being flat on a page. So when you see this Fischer projection, right, this flat molecule, you have to interpret it as follows, okay? It's telling you that Z is going behind the plane of the paper, or in our case, the screen, and Y is going towards the back, right, behind the plane of the screen, and our X and our W are sticking out at us. They're sticking right in our face, okay? C, our carbon, is in the plane of the screen. All right, so behind when they're in this position, okay? So the Z and the Y always, right, behind, and our W and our X are coming out at us, poking out at us. All right, so this is our Fischer projection. Bonds that point again above the page, okay, are shown as horizontal lines. All right, so these bonds here, okay, that point above the page because they're wedged, right, are horizontal lines in our Fischer projection. There they are. And any bonds that curve behind the page, right, behind and below, all right, are shown as vertical lines. Okay, that is what or how we interpret a Fischer projection. All right, so why are we talking about these Fischer projections? Well, direct application to sugar molecules, Fischer projections and sugar molecules. All right, so you're keeping this in mind. All right, this is how we get a Fischer projection. Okay, this is what one looks like. Okay, in a Fischer projection, all right, which we use Fischer projections to draw carbohydrates, the aldehyde or the ketone carbonyl group of a monosaccharide is always going to be placed on the top of the page. Okay, so that means, all right, that the aldehyde or the ketone group is always going to be this Z right here, okay, at the top of the page or at the top of your Fischer projection of your molecule. For example, let's look at glyceraldehyde. Okay, glyceraldehyde is a monosaccharide. Conventional representation for glyceraldehyde, right? So that means with dimension, 3-dimension, would be like this. Looks familiar, right? Okay, we're going to do exactly what we did with the molecule, the fake molecule on the previous slide. We're going to flatten this out into a Fischer projection. Okay. All right, the aldehyde's going to be near the top, okay, or the ketone, as we said. All right, so there it is. All right, and those that are horizontal are coming out at us. Those that are vertical are going away from us. Okay, so the Fischer projection of glyceraldehyde would simply be as follows. Okay, we're going to take away these wedges and dashes, right, and just put horizontal and vertical lines, right? So again, the horizontal ones, they're poking out at us, right? And that carbon is in the plane of the screen, and then our aldehyde and our CH2OH, they're going behind the plane of the screen. That's the Fischer projection. So when you see a monosaccharide, any monosaccharide written like this with just horizontal, vertical lines, that's what they mean. Okay? All right. More Fischer projections of sugar molecules. Monosaccharides, in addition to the classifications, right, according to functional group and number of carbons, monosaccharides are divided into 2 families. The D form and the L form of the sugars. For instance, here we have glucose again. Okay, there are 2 forms of glucose, D-glucose and L-glucose. There are 2 forms of every single sugar, all right? The D form is typically the one that we find in nature, okay? What does it mean when we say the D form of a particular sugar, such as the D form of glucose? Well, that D, right, designates the OH group on what is called a chirocarbon furthest from the carbonyl. Okay, so what's a chirocarbon, right? Chirocarbon is one with 4 different groups attached to it. All right, 4, they got to be different. All right, so furthest from, so here's our carbonyl. Here's one with 4 groups, 4 groups, 4 groups, 4 groups. Okay, this one does not have 4 different groups. All right, so we're talking this guy right here. Okay, so the chirocarbon, the carbon with 4 different groups that is furthest from the carbonyl. And it, this OH, right, okay, when it's D, it comes out of the plane of the paper, right, because these point out, and it points to the right. So notice this guy's to the right, okay? An L form, on the other hand, okay, again, the OH, we're going after that OH on the chirocarbon furthest from our carbonyl. So here's our carbonyl, right? Here's our carbonyl, right? And we're coming furthest, so we're looking at this particular one right there, okay? And notice what way our OH is. It's to the left. Right, so it's the L. This one is to the right, so it is D. Okay, so the L and the D. Okay, and again, like I said, it's the D form that that usually we find in nature. All right, so L and D, that's what those mean. So let's take a look. All right, with all of this information, let's take a look at some of the important pentoses and hexoses and their derivatives. Right? Now, we've heard this term before when we talked about carboxylic acids, right? Carboxylic acid derivatives. Esters were carboxylic acid derivatives. Amides were carboxylic acid derivatives. In other words, they were made from a carboxylic acid. So monosaccharide derivatives mean they're going to be made from a monosaccharide. All right, so some of the more important pentoses, 5 carbons, right, and 6 carbons, sugars, hexoses. And we start out with our glucose, D-glucose. All right, D-glucose is one of the more important 1, 2, 3, 4, 5, 6 aldo hexoses. It is known commonly as dextrose or blood sugar, and it is the most important monosaccharide in human metabolism. So you should be familiar with what D-glucose looks like. All right, and here we have D-fructose. Let's look at it. Let's classify it. We notice that it is a ketose. How many carbons? 1, 2, 3, 4, 5, 6. So this is the other thing too. Some of the structures, remember, where they cross here, you have to understand, hey, there's a carbon here. They're just not showing it. It is understood. Some of the crazy things that they do. Okay, so you can always write them in. All right, so D-fructose, again, remember what D means, that OH right here, right on that chiral carbon furthest from the carbonyl, points to the right. D-fructose, also known as fruit sugar, it's the most common natural ketose. All right, for instance, honey, right? You're all familiar with honey. It's 40% fructose. All right, so did we classify it? 1, 2, 3, 4, 5, 6. So it is a ketohexose. All right. Okay, so those are the 2 most important ones that you need to be familiar with right now. Let's look at some monosaccharide derivatives. The first one we're going to look at is something called a deoxy sugar. Deoxy sugars. In deoxy sugars, a hydrogen atom replaces one or more of the hydroxyl groups in a monosaccharide. For example, let's start with ribose. Okay, so this is D-ribose. So here is yet another monosaccharide, right? D-ribose is 1, 2, 3, 4, 5. So it's an aldopentose. Okay, again, remember where there's that cross right there, we have a carbon. Okay. All right, and here we have D2-deoxyribose. So what does it mean to be deoxy? We said that we're going to replace one or more hydroxyl groups. So let's take a good look at this and see what's different. Aldehyde's the same, right? We come down to that first carbon, and we had an OH here. We now have a hydrogen. So we have replaced one of our hydroxyl groups. This one's the same. This one's the same. Everything else is the same. We have replaced one hydroxyl group, and then it's called a deoxy sugar. So D-ribose we have here, and its derivative D2-deoxyribose because it's on the second carbon. Okay. Deoxy means -1 oxygen atom. Okay. And this is found in in various coenzymes and in DNA, deoxyribonucleic acid. All right, we move on to amino sugars. In amino sugars, one of the OH groups of the monosaccharide has been replaced with an amino group. Remember what an amino group is, an NH2 group. D-glucosamine would be an example of an amino sugar. So here we see D-glucosamine. So it's simply a glucose molecule in which, notice, we have taken and replaced a hydroxy group on glucose with an amine, and we have D-glucosamine. Okay, it's an amino derivative in which the amino group replaces a hydroxyl group of the original monosaccharide, in this case, glucose. All right, our next derivative, sugar alcohols. In sugar alcohols, or alcohol sugars as they're sometimes called, the carbonyl group of a monosaccharide has been replaced or reduced to an alcohol. All right. An example of a sugar alcohol or an alcohol sugar is sorbitol. You've all heard about sorbitol, right? Sorbitol is used as a sweetener. So here's our sorbitol. Okay. And we look at it, it's polyhydroxy, right? But there's no carbonyl. So the carbonyl has been converted to an alcohol. Now, back in our chapter on aldehydes and ketones and alcohols, we learned that we could start with a carbonyl, right? A carbonyl compound can be reduced, right? And when it's reduced, we produce an alcohol. So the reduction of a carbonyl group in an aldehyde or ketone is what produces alcohol sugars or sugar alcohols. So in this case, right, what do we have here? We have a primary alcohol. How do we get a primary alcohol? Well, we start with an aldehyde. Reduction of an aldehyde with hydrogen, right, and a metal catalyst is going to give us that primary alcohol, right? Okay. If you don't remember, go back to your chapter. Okay. All right, our next derivative of a monosaccharide are the carboxylic acid sugars. In carboxylic acid sugars, right, again, think, right, remember our aldehyde and ketone chapter, right? Aldehydes and ketones could be converted into carboxylic acids. So in carboxylic acid sugars, an aldehyde or even, remember, an alcohol group could be oxidized, right, into a carboxylic acid. So an aldehyde or an alcohol group of the monosaccharide is going to be oxidized to form a carboxyl group in a carboxylic acid sugar. Here is an example of a carboxylic acid sugar. It's D-gluconic acid. So D-gluconic acid, we notice we don't have the aldehyde, right? The aldehyde has been oxidized, addition of an oxygen, right? Okay, and recall, again, we're going back to an earlier chapter. This is why we learned it. The oxidation of an aldehyde carbonyl produces a carboxylic acid. And so if we do that with a sugar, we're going to get a carboxylic acid sugar. So we start with D-glucose. We treat it with an oxidizing agent, right? And when we treat an aldehyde with an oxidizing agent of some sort, we add oxygen, right? The addition of oxygen, loss of hydrogen, right, to that carbon gives us the carboxylic acid sugar. Oxidation of monosaccharides. Recall earlier chapter, right? Benedict's solution, Benedict's reagent. Benedict's reagent was a copper compound that would oxidize only aldehyde groups. So if we're applying this to carbohydrates, right, we're talking about aldoses. Benedict's reagent then, right, since it's specific to aldehydes, it's going to be specific to aldoses, right, and not alcohols. A sugar then that reacts with Benedict's solution is going to be reduced, okay, or it's going to reduce your copper, right? So it's referred to as a reducing sugar since it reduces your copper. The example that we talked about back in our earlier chapter was glucose. And now we know all too well what glucose looks like, right? It's an aldohexose. So here it is. It has an aldehyde group in it. When we treat D-glucose with Benedict's reagent, okay, Benedict's reagent is an oxidizing agent. So it's going to oxidize the aldehyde group. It's specific for aldehyde groups. It's not going to hit any of these alcohols. It will oxidize that aldehyde group right here in our D-glucose. What does it oxidize it to? A carboxylic acid. All right. And at the same time, remember what it does. It goes from a blue to a brick red. That's the color change that we see here. Okay. And so glucose is called a reducing sugar because it reduces the copper. Note, real important note, when we talk about monosaccharides, some ketoses also give positive results for this Benedict's test. How can that be? Right? It's specific for aldehydes. Well, this is because the ketoses, some of the ketoses, rearrange to aldehydes when they are put in this strongly basic Benedict solution. If you go back and look and see what the ingredients, what the other things are in the Benedict solution, it's basic, strongly basic. So in the presence of the base, some of our ketoses will rearrange to aldehydes. And an example of a ketose that gives a positive Benedict's test is D-fructose. Okay, D-fructose is a ketose. Okay, when we treat D-fructose, which is a ketose with Benedict's solution, it will rearrange. Okay, some of it will rearrange to an aldehyde. Okay, notice what happens. Okay, that carbon goes to an OH and an aldehyde up here. So this is a rearrangement. And since you are getting some D-glucose out of this, it will then reduce. Okay, and it will also give you some of the opposite, right? If we flip that around, we get D-mannose, and it will then give you a positive Benedict's test. Okay. Alrighty. These are oxidizable aldehydes. So just be aware of that. All right. Yes, it's typically just the aldoses, but some ketoses such as D-fructose also give positive Benedict's test. Okay. All right. where do we move now? We move to cyclic structures. So remember monosaccharides, right? They could have the polyhydroxy, aldehydes or ketones with at least 3, minimum of 3 carbons, right? Maximum of 7, all right? Turns out that monosaccharides with 5 to 6 carbon atoms form stable cyclic structures. How does that happen? Well, the hydroxyl group on carbon 5 reacts with the aldehyde or the ketone group. And when that happens, you end up with either a stable 5 or 6 carbon cyclic structure. Let's look at this in a little bit more detail. Monosaccharides and these cyclic forms. How does it happen? Well, a hydroxyl group. Okay, you all know what a hydroxyl group is, an alcohol, right? Okay, can react with a carbonyl to form what's called a hemiacetal. So let's look at this reaction. Okay, hemiacetals, right? So what are we saying? They are made by the reaction of an aldehyde and an alcohol. Right? Aldehyde, right, and an alcohol can combine. So we're color coding so that you can see what happens here. All right, when an aldehyde and an alcohol combine, we end up with what is called a hemiacetal. All right, so here's our carbon of our carbonyl. All right, the hydrogen from the alcohol gives you an OH. We convert our carbonyl into a hydroxyl group, right? And we also have our OR, right, from our alcohol. So we have both of those elements in there. So a hemiacetal, it contains a carbon atom, as we said, right? Carbon atom, here's our carbon atom, and that carbon atom is bonded to an OH and an OR group. That is what a hemiacetal is. Okay, so remember that structure. Okay. If you have the carbonyl, the aldehyde, right, and the alcohol in the same molecule, one's at the top, like in a monosaccharide, right, and one of the alcohols is down at the bottom, okay, the same reaction can occur, and you're going to join the top to the bottom. So you're going to have a cyclic hemiacetal. For example, let's go back to our good friend D-Glucose. Okay, D-Glucose, we've used it so many times that you should commit to memory the structure of D-Glucose, right? 6 carbons, aldohexose, right? Aldehyde at the top, all right? Right hydroxyl, left hydroxyl, right, and then this CH2OH, okay? So keeping in mind what we said about forming a hemiacetal, right? An aldehyde and an alcohol. Look what we have here, right? We have an aldehyde and we have an alcohol, right? Okay, 5 or 6 membered ring, right? If you've got both of them in the same molecule, right? It can react with itself and form this hemiacetal, okay? And this hemiacetal will be cyclic. So let's bring those together, okay? All right, remember what happens, right? This hydrogen is going to come up here and give us an OH. And then this oxygen is going to join with that carbon. So here it is, right? The oxygen to carbon. Here is the hemiacetal carbon. right? Remember what we said about a hemiacetyl carbon. It's bonded to a hydroxyl group, right? There's our hydroxyl group. And here's the OR. It's just, here it is right here. OR, right? Right there. It's just all on the same molecule. Okay? A cyclic hemiacetal. So, cyclic forms of monosaccharides are usually drawn using what are called Haworth projections. In a Haworth projection, what we're doing, the ring that just formed, all right, is viewed from the side and it's viewed at an angle. For instance, okay, so remember when we formed that cyclic hemiacetal, right, we had an oxygen, right, okay, we formed a bond. So this is what they look like. This would be the 5-membered, or 6-membered ring, right, hemiacetal, and this would be a 5-membered. Remember, those are the two most common form. All right. In a Haworth projection, the edge of the ring that's closest to us, the viewer, right, is typically emboldened, all right, with a bold line, just so that you get perspective, so that remember, bold lines means it's coming out at you. And so this oxygen is away from you, as is this one. Okay. All righty. What else? The cyclic structure, right, of a D-isomer. Remember, D-isomers are the most common ones, right? They're the ones we find in nature. Is going to additionally have the final CH2OH group located above the ring, right? So we're going to add on things, right? So these are all carbons, right? Sticking out at us, right? Carbon for each one of these. Here's our hemiacetal OR bond, and then there's a CH2OH, and it is above the ring. It's always located above the ring. Substituents, right? We're not seeing substituents yet. Well, substituents on the ring in one of these Haworth projections are going to be either up, down. Substituents are hydrogens and hydroxyl groups, right? So they're going to be up or down, all right? So we have to add those to the mix here. But keep in mind that sometimes when you look at these Haworth projections in books or online, Haworth projections can be drawn either with or without some of the hydrogens on the ring. Sometimes all they do is to put the OHs in, all right? And if you see them like that, you got to know that the hydrogen is there too, because every carbon has 4 bonds to it, right? So sometimes they just leave out the hydrogens and only show the hydroxyl groups. All right. So let's look at a completed, a finished Haworth structure for D-glucose. There are 2 of them. These are the Haworth structures for what we call the anomers of D-glucose. Right? Note, okay, let's note all the things that we talked about. Okay, so we see the OR bond, right, of the hemiacetal. There it is. Our CH2OH is up in both of them. We're showing the bonds coming out at us 4 dimension in both of these. Right? Notice we're not showing all of the bonds. We're just showing the hydroxyl group. I said this is very common, right? So always the CH2OH is up. Okay, and then in D-glucose, this one here is down, right? Up, same, right? Down. And then here we're seeing a difference. Okay, notice in one hydroxyl group is up, one is down. All right, what gives? Well, these we said are anomers. Anomers are a pair of cyclic hemiacetals, okay, with the OH on the hemiacetal carbon in different positions. That's what we're seeing here, okay? This is that hemiacetal carbon, Okay, right here. Let's put it in. Right? Hemiacetal carbon. Remember what is bonded to a hemiacetal carbon? An OH group, right? Okay. And what? An OR, right? And so there's our OR. So it has an OH and an OR. Okay, so the hemiacetal carbon. The only difference between these two D-glucose molecules is that one OH is down and one is up. These are called anomers. Okay, the one with the OH pointing down right here. Okay, this is pointing down. Okay, this is the alpha anomer. Okay, OH pointing down, alpha anomer. And the other one right here with that OH, whoops, pointing up. All right, well, all right, I'm going to take that out. I'm going to point to the carbon. So the carbon, right, with the OH pointing up is called the beta. All right, beta anomer. Well, I think I can erase this actually. Oh, look at that, gone. Okay, all righty. So alpha and beta anomer. So every single time we end up, no matter what Haworth projection we're looking at for what monosaccharide, you're always going to have these two anomers. You're going to have one where the hydroxyl group points down, one where it points up. When it points down, it's alpha. When it points up, it's beta. Okay? Alrighty. Nomenclature for these cyclic forms of monosaccharides. All right. So we're going to add another layer to our nomenclature. All right. The cyclic forms of monosaccharides can and often are named as derivatives of heterocyclic ethers. Remember, we had this term heterocyclic. All right. In our previous chapter, we talked about nitrogen heterocycles. All right. So they were rings, carbon rings, in which one of the carbons had been replaced with a nitrogen. All right. So heterocyclic ethers, meaning we're going to have one of the carbons replaced with an oxygen. All right. So 5-membered ring ethers are known as furans. Okay, so this is furan. And you notice when we were looking at those Haworth projections, right, if we had a 5-membered ring, it sort of looks like this furan, except for there's no double bonds. All right, and 6-membered ring heterocyclic ethers are called pyrans. All right, Pyran. All right. And again, sort of looks like our 6-membered ring monosaccharide, the Haworth projection, except for, again, we didn't have double bonds. So, so we're going to name them based upon their similarity to these furans and pyrans. All right. Okay. So I'll inform you when we see these names. You're going to see them very shortly. All right. So another interesting fact about monosaccharides, D-glucose, okay, in a solution, the open chain and cyclic forms of a monosaccharide are in equilibrium. All right, so we've looked at the open chain form, and we have seen how it forms a hemiacetal and you get a cyclic form. So in solution, if you have a solution of a monosaccharide such as D-glucose, right, your open chain form is going to be in equilibrium with your cyclic form. So here we go. Let's imagine this. This is what we're saying is happening. Let's imagine we have a solution of D-glucose. Okay? Starting at the center, this is our open chain form. All I've done here is to take and put that D-glucose on its side. all right, as opposed to having it straight on up. Okay, and it's easier to see how it forms your cyclic form. All right, so what happens here, you might remember back when we talked about alkanes, we said that between carbon-carbon single bond, there's free rotation. Remember I showed you a model back then? So there's free rotation about this bond right here. So if it rotates, okay, we're going to get this configuration here with our carbonyl pointing down, carbonyl oxygen pointing down. If it rotates, it's going to be pointing up. Okay. All right, so that's all that's going on here. So that free rotation, all right, gives us these two forms, all right, but they're both open chain. And we saw what happens, right, is that we can get a reaction between the alcohol, right, down here, and that carbonyl, and we form a hemiacetal, right. From one of these, we get the alpha, okay, D-glucose, where the hydroxyl group is down, and if it closes with it in the other position, we get the beta. All right, so the open chain form, okay, is in equilibrium with the closed cyclic form. All right, and when they look at how much you have at equilibrium of all of these, they find out that there's only a very little bit of the open chain form, and most of it is the beta D-glucopyranose. Okay, this process by which a very small amount, right, of open chain form, just a trace, is in equilibrium, right, equilibrates with the cyclic forms, both of them, is known as mutorotation. Okay, so we say that monosaccharides, right, such as D-glucose, undergo mutorotation. Okay, they close, right, and we get both of the anomers, all right, and they're all in equilibrium with one another, meaning they go back and forth, back and forth, back and forth. But at any moment in time, right, we seem to have a preponderance of the beta form. And that's because the most stable form of glucose is that beta D-glucose, okay? So remember how we said earlier that oftentimes we add another layer to the name, all right, based upon the fact that it looks like a pyran, right? So notice the names here, all right, alpha D-glucopyranose, okay? They're telling you that it is the six-membered ring with the oxygen in it, okay? So that's alpha D, this is beta D-glucopyranose, okay? The pyran telling you that it's similar to pyran, so it's the six-membered ring with the oxygen in it, okay? Alrighty. So you might be wondering, how in the world do you get from that open chain form to the cyclic form? Well, let's take a look. We'll give you a quick lesson on how to do it, all right? So this is glucose, okay, our polyhydroxyaldehyde. What we've done is we've numbered, right, our carbons. The aldehyde's always number 1, all right? How are we going to get from that to that cyclic pyranose form? We're going to take the first step is going to be to flip it on its side, turn it to its side, right? And then coil that CH2OH up, okay? So that's what we mean here. Flip it on its side, okay? And remember what we said in this six-membered ring, pyranose, right? That CH2OH is always up in the Haworth projection. Notice what we're doing. We're emboldening these lines just as we said we do in a Haworth projection. And then you're perfectly set up for that reaction between the hydroxyl group, right, on carbon 5 and our carbonyl of our aldehyde, right? We're going to move this hydrogen on over, okay? And there we go. We end up with the alpha form with the hydroxyl group down, or the beta form, depending, all right? And there are our Haworth projections. So it's really not too difficult to do. It just takes some practice, all right? More on our cyclic form. Let's do another one. Let's do a practice. Let's take another monosaccharide. Let's take galactose, D-galactose. And again, remember what the D means, right? That OH on the carbon furthest from your carbonyl is pointing to the right, and there it is. So it's D-galactose, right? Why is this galactose and not glucose? Because those hydroxyl groups are in different positions, okay? Alrighty, flip it on its side. All right, knock it down on its side. Imagine doing that. Coiling up, that's CH2OH. Closing the ring, right? Putting that OH down. And then you have alpha D, galacto. Notice the name, pyranose, right? Pyranose or pyranose, all right? And who else do we have? That OH could point up, in which case we're going to have beta D, galacto, pyranose or pyranose, okay, depending upon who you listen to, okay? Alrighty. The open chain form, all right, this is what we're looking at here. This is the open chain form, right, of D-galactose. And then what have we done? We've knocked it on its side, turned up that CH2OH, closed it up, and we have its cyclic anomers. All right, let's do another example. Let's take D-ribose. Okay, D-ribose. It's an aldose. 1, 2, 3, 4, 5, right? So it's an aldopentose. Okay. We're going to take this and we are going to form a cyclic, right? Hemiacetal. This is what we're going to join. Okay. Right there and there. Right. So it's not going to be a 6-membered ring. It's going to be a furanose. All right, so there's that name again, furanose. It's like furan, right? The 5-membered ring. Let's see if we can do this. Okay. So we're going to knock it down on its side. Okay, knock it down on its side. Right, rotate it down this way, flatten it out. Wind that CH2OH up. That's what our rules told us to do. So in this one, we're showing that same thing like we did with glucose earlier, right? We can have that carbonyl group, all right? The C double bond O point down or up. That's how we end up with the 2 anomers. Okay, let's close things on up. Let's bring this on over, right? Let's transfer our hydrogen to here. There it is. Okay, here's our anomeric carbon. Our OH is down, right? So this is the alpha D ribofuranose. And in this one here, there's our anomeric carbon. That's what it's referred to. Our OH is up. So this is our beta D ribofuranose. Okay, and again, take a look at that name. Remember what that means. Okay, 5-membered ring. It's telling you what it looks like. Okay, all right. Okay, so we've seen some of the more important monosaccharides. Moving on, let's go to the oligosaccharides. Oligosaccharides. They are short polymers containing between 2 and 10 monosaccharide units, or residues as we call them. Among the oligosaccharides, we find several important disaccharides. In disaccharides, and as well as these other oligosaccharides, the residues or monomers, All right, they're bonded to each other with what we call glycosidic bonds. What's a glycosidic bond? It's an ether linkage. All right, remember what an ether is, right? An ether linkage is R, right? O, R, right? Meaning we have an oxygen sandwiched between two carbons. So we're going to link two monosaccharide units with an ether, right? An ether bond. That's what a glycosidic bond is. It's an ether linkage formed when an acetal is made by reacting a hemiacetal and a monosaccharide with a hydroxyl on another sugar. All right. We're going to be looking at disaccharides. The important disaccharides that we're going to be looking at are maltose. Maltose is a disaccharide that has got two glucose units linked together, right? We're also going to be looking at lactose. Lactose is another disaccharide. Its two monomers, glucose and galactose. And our last one that we're going to look at is sucrose. It's a disaccharide which is made up of glucose and fructose. So we've looked at all of these monomers. You should be familiar with them, all right? Now we're going to begin linking them together. Let's begin with our maltose, okay? Glucose and glucose. Maltose, we said, is a disaccharide of D-glucose. So two D-glucose residues or units, all right? And they're linked together with what we call an alpha 1,4 glycosidic bond. All right, so let's look at this. Let's take two glucose units. We'll look at them in their cyclic forms. Okay, all right, two glucose units. And we have our OH groups going down. All right, so they're alpha D-glucose units. We're going to form what's called a glycosidic bond. All right. Why did we call it an alpha 1,4? Because our OHs were in the 1,4. Our OHs were alpha, both of these, right? Okay, alpha on both of them. And the linkages between one, the OH on one, and the OH on 4 on the other. Okay, so alpha 1,4 glycosidic bond right there. And what else do we get? We also get water when these two form. All right, when two alcohols join to give you an ether linkage, we get water, and that is our maltose. Okay, so you should be able to recognize an alpha 1,4 glycosidic bond. Okay, we move on to lactose. Lactose is a disaccharide that we find in milk. It consists of, as we said, galactose and glucose, all right? And so they're going to be linked together by a glycosidic bond, and it is a beta 1,4 glycosidic bond, okay? So the beta is telling us that anomeric, the position of that anomeric hydroxyl group, right? It was pointing up, okay? So beta comes from that, right? Remember, alpha, beta designate the position of it, that OH on the anomeric carbon. All right, so beta 1, and then where's it linking? To the hydroxyl group on the 4th carbon. Okay, so the galactose, right, and the glucose. So it's the galactose beta, right, hydroxyl group. Okay, to the number 4 on the glucose residue, right? So you might, maybe some of you might be lactose intolerant or know someone who is, or you have heard of someone who's lactose intolerant. Lactose intolerance is the inability to hydrolyze lactose. Right, hydrolyze meaning break apart lactose into its monomers, which would be galactose and glucose. So if someone's lactose intolerant, they lack the enzyme that cleaves this bond, this one beta 1,4 glycosidic bond. All right, and our third disaccharide is sucrose. Sucrose is also known as table sugar. It's a disaccharide with, we're going to say, 2 twists to it. Different residues, in other words, different monosaccharides, right? And in addition to having different monosaccharides, it has no hemiacetal. The glycosidic bond in glucose is formed between the hemiacetal carbon of alpha glucopyranose and the hemiacetal carbon of beta fructofuranose. Whoa, that's a mouthful. Let's look at our structures. Okay, so a pyranose, which is 6-membered ring with an oxygen, right? Glucopyranose, so that's glucose, and then fructose, but our fructose is 5-membered ring, so that's telling us a lot about what it's going to look like. All right, so this funky type bond here is a alpha beta 1,2 glycosidic bond. Let's look at it. All right, we're going to see these different elements. We're going to see the glucose, the glucopyranose. Okay, so it's formed between, as we said, the hemiacetal carbon of alpha glucopyranose. So here we see the pyranose, the 6-membered ring. Okay, here's the anomeric carbon. Okay, the one that formed the hemiacetal. It was an alpha, right? There it is, right there. Okay, pointing down. And then it formed this glycosidic bond, okay, with the hemiacetal carbon. Here's the hemiacetal carbon, all right, of fructofuranose, beta fructofuranose, all right. Here it is, beta. It was pointing up. Okay, so alpha coming down, right? Beta coming up. So we call it an alpha beta 1 because it's the 1 carbon here, the 2 carbon here, all right? Glycosidic bond. And so that gives us our table sugar, all right? So it's a disaccharide, 2 different residues, and the twist to it, it's an alpha beta glycosidic bond. Okay, we move on. Polysaccharides. Polysaccharides, as we saw earlier, contain 10 or more residues, okay, or monosaccharide units. All right, there's 2 different types of polysaccharides. A homopolysaccharide. In a homopolysaccharide, all of your residues, your monosaccharide units, are the same. Okay, same monosaccharide each time. In a hetero polysaccharide, the residues are built from more than one type of monosaccharide. Primary functions of polysaccharides are to provide structure, such as in cellulose, which is an example of a polysaccharide that we'll look at, or to store energy, as in the case of starch and glycogen. The important polysaccharides that we're going to be looking at in this chapter are starch, 2, amylose, and amylopectin, and glycogen. In addition to those, we're also going to look at cellulose. And we're going to begin with our last one. Okay? Cellulose. It is a homopolysaccharide. So that means it's going to have the same unit, repeating, right? So it consists of a long linear chains of glucose residues or glucose monosaccharides all linked together. All right, so how are they linked? Well, in cellulose, they're all linked by beta 1,4 glycosidic bonds. Okay, so totally different than our maltose, right? Beta 1,4. Here's a beta 1,4. Here's a beta 1,4. Every single one. And remember, this repeats on and on. All right. So we only show a short section of it typically because we don't want to be drawing 10 and more of these. Okay. All righty. So beta 1,4 glycosidic bonds. Cellulose is so strong, and the reason for its strength comes from the fact that the linear chains of glucose can form a lot of hydrogen bonds. Remember, it's polyhydroxy, and hydroxyl groups can form hydrogen bonds. So imagine a whole lot of these glucose chains, all right, and they can form hydrogen bonds with adjacent chains. And when they do so, what happens is you end up with sheets of the polymers. Right, something like this. All right, so here we see chains, right? Okay, and in a chain we can see hydrogen bonding occurring, right, between the hydroxyl groups, and that gives glucose or cellulose its strength. Wood, right, is about 50% cellulose, and wood is pretty strong. Okay, so we know that horses, cows, and of course termites, all right, all eat plants, right? How do they digest this strong polymer, all right? Well, they have bacteria, all right? Bacteria in horses, cows, and termites have the enzyme called cellulase, which this enzyme is able to hydrolyze. Remember what hydrolyze means. It means break apart with water, okay? These beta 1,4 bonds. We can't do that super easily, okay? So we don't have cellulase to be able to break it apart. All right, we move on to starch, okay? Starch is a homopolysaccharide also. It is used by plants to store energy. There are two components to starch. One is amylose, and the other one is amylopectin. Let's look at both of them. Beginning with our amylose. Amylose contains chains of glucose monomers, all connected together by alpha 1,4 glycosidic bonds. So here we have glucose. We recognize it again. Quite a difference, though, between this and our cellulose, right? Remember, we had beta 1,4 glycosidic bonds. These we see clearly, the OH down, right? So these are alpha 1,4 glycosidic bonds. Unlike cellulose, amylose chains are not linear, but instead what they do is to coil into a helix, right? So their structure, their tertiary structure is much different. Amylopectin. It is the other component of starch. Amylopectin, similar to amylose, except for it contains glucose residues linked by alpha 1,4 glycosidic bonds. But in amylopectin, this chain branches through an additional alpha 1,6 glycosidic bond. So amylopectin has some of the parts of amylose. Here's the part of amylose, right? The glucose units that are bonded together with alpha 1,4 glycosidic bonds, right? Amylopectin differs because every so often we have thrown in there another glucose unit that's joined with an alpha 1,6 glycosidic bond. All right, so 1 on one and the 6 on another. Okay, so we throw that into the mix, and that changes things immensely. Our structure that we're talking about then for amylopectin is something like this. Okay, so we've got the long chains of glucose, and then every so often we're going to end up with a branch. Okay, a branch to another glucose. All right, and so we end up with branches as opposed to long, thin sheets. Okay, so this branched polysaccharide, the branching makes it a little bit easier because we can break down simultaneously at numerous points, and that then allows the glucose residues and their energy that they contain to be released a whole lot more quickly. All right, glycogen is our last polysaccharide. It's known as animal starch. It is similar to our amylopectin, right? Except that the chains in glycogen branch more frequently. Okay, so that's the only difference. It's going to have the 1,4 alpha linkages, and then it's going to have the 1,6, except for we're going to see them more often. Right. So remember what our amylopectin structure resembled. Okay. The long chains and then some branching to another one. Okay. All right. Glycogen. Okay. Even more branching. All right. Even more branching. So amylopectin's to the right. Your branching might occur every 25 to 30 residues. All right. But with our glycogen on the left, the branches are occurring more often. Every 8 to 12 residues we have branching, all right? Which means that we can break and hydrolyze them and get even more glucose for energy, okay? All right, we're nearing the end of this chapter, the last topic, carbohydrate metabolism. This is the little bit, right, from chapter 18, section 2, all right? Digestion of carbohydrates. It begins in the mouth. Enzymes that are produced by the salivary glands are capable of hydrolyzing some of those alpha glycosidic bonds, all right? And remember what hydrolyze means, right? We looked at hydrolyzing different functional groups, right? Okay, and it was breaking them down with water, all right? So the same thing happens with our carbohydrates. All right, those alpha glycosidic bonds in amylose and amylopectin, right, get hydrolyzed. And what's that going to do? That's going to give you smaller pieces. So that's going to produce maltose, glucose, and smaller polysaccharides known as dextrins. All right, so what's the next stop after that? It's the stomach, and the pH in the stomach is low. The low pH of the stomach totally stops carbohydrate metabolism. And then it's picked up a little bit further down the line. It resumes in the small intestine. And the reason for this is because the pH is now a little bit higher. It's now just slightly basic at about 8. And it's in the small intestine where enzymes that are produced in the pancreas will then do a whole lot more hydrolyzing, okay, breaking down these alpha glycosidic bonds, right? The 1,4 and 1,6. They hydrolyze the remaining dextrins and into maltose and glucose. And then come in our carbohydrate-specific enzymes, such as maltase, all right? Enzymes always end in this ASE, all right? Maltase, lactase, sucrase. they come in and they hydrolyze those disaccharides into their residue, their monosaccharides. And then it's those that are absorbed into the bloodstream through the intestinal walls. All right, so that's our written explanation of our carbohydrate metabolism. We're going to close out this chapter with a visual, a good visual of what exactly happens. Okay, and here we have the very last slide. All right, shows the course of carbohydrate metabolism from our polysaccharides, right, in the mouth. Our salivary amylase, right, breaks things into maltose and glucose and dextrins, which are smaller pieces, all right. Stomach pretty much stops carbohydrate metabolism, but it's picked up again in the small intestine. Dextrins are broken into maltose. Maltose is then hydrolyzed with maltase into its 2 units, glucose units. Lactose is hydrolyzed with lactase into galactose and glucose. And our sucrose that we learned about, right, is hydrolyzed with sucrase to fructose and glucose. And these are then taken up into the bloodstream and brought to where they're needed. And with that slide, the end of our discussion for Chapter 13 and Chapter 18, Section 2.